the talk is going to be on Jax, which is Google's latest framework for high-performance computing. Specifically, the main focus is around ML, but really it can be adopted for any form of scientific computing that needs to run at speed. There is a lot to cover in this talk, so I'm going to ask to just save questions till the end. Also, because there's a lot to cover in a short amount of time, I'm not going to be able to go too in-depth on any of the topics covered, but please reach out to me afterwards and we can talk about any deeper questions you have. So with that, let's get started. So quick overview with the state of ML where we're at the minute. So this year alone, we saw that DeepMind used AlphaFold 2 to add over 200 million known protein structures to their open database. We now have realistic image generation from multiple sources such as DALL-E 2, Imagen, and the open source Stable Diffusions. DeepMind again was able to successfully control nuclear fusion plasma in a tokamak reactor using reinforcement learning. And finally, Alpha Tensor is the first AI capable of discovering novel algorithms, but also effective algorithms. And this was all just in 2022. The rate of AI advances and breakthroughs are speeding up. And also, if you notice, a lot of these advances that I mentioned here are directly from Google or collaboration with Google. So they seem to have a pretty good sense on how to do fast breakthroughs, and it's worth looking at what they think the future is. So with that in mind, enter Jax. So like I said, Jax is Google's new framework, relatively new, it's been maybe a year now, or maybe a little more, but Jax is their high-performance numerical computing library, and it focuses on generating optimized code as simply as possible, and that is the main thing, is simplicity and being able to very, very quickly iterate and experiment and put out these breakthroughs for research. So Jax has four main pillars or things to remember about it. First off is XLA compilation, reproducibility, SPMD, which essentially single process multiple data, and finally AutoGrad, which is just automatic gradient differentiation, key pillar for any machine learning framework. So why do we care? TLDR, Jax is really fast. You can go home now. It runs fast, it scales fast, and it implements fast. With a small caveat that you're able to implement really fast once you get used to working in Jax, but it's fine, you'll be fine. So, Jax has all these cool things, and we'll go through these in detail. But the main question I get asked, and people generally ask, is why is this special? None of these kind of technologies or ideas are anything new. And you're right. So the likes of Tensorflow and Pytorch, they all have this. You can do XLA compilation, you can get reproducible results, you can distribute your training with a single model, and they obviously all AutoGrad would be a joke otherwise, but they all have this. However, they don't do it as well as Jax does, because Jax has this ingrained in its DNA from the ground up. Everything you do in Jax is to fit this goal of being able to quickly scale and optimize your training. So, how is Jax so fast? Well, first up is the XLA Compiler. So this really deserves a talk all by itself, so I'm going to give a very brief overview and apologize if it is not doing it justice, but I'll do my best. So what it is linear algebra compiler, XLA, accelerated linear algebra. So linear algebra compiler that fuses low-level operations into a single computational graph, and with this we can apply further performance optimization. This allows us to increase execution speed by executing operations on the accelerator all at once instead of sending off individual operations to the accelerator one at a time. It improves memory reductions by analyzing and scheduling memory uses, and this is also going to bring its own speed improvements. And finally, it is portable. If you compile your code down to XLA, you can then run that on any hardware accelerator. If you have new proprietary hardware accelerators, you can easily write a backend for XLA for that code to run on it. It makes it all very, very easy. So on the left here, we have some performance graphs from Google, and this is showing different speed improvements. I believe this is running BERT for their tests, but we can see with no XLA, it is very, very small throughput. Once we introduce XLA compilation, there is a massive increase, and then when we apply further ML techniques such as gradient accumulation, there's a massive increase again. And on MLPerf, which is a performance benchmark suite for benchmarking throughput and performance, Google reported being able to get a 7x performance improvements in BERT and a 5x batch size improvement, which is huge. So for reference, BERT is one of the big breakthrough in large language modeling, and a lot of the latest research is then off the back of the improvements for BERT, and they're all very large and they all take a very long time to train. So any speed improvements at all is huge. Next up is transformations. So the main thing with Jax is that it provides multiple transformation functions, which can basically be wrapped around your own code and functionality and transform it for improved computation and scalability. So these include Grad for gradient differentiation, JIT for JIT compilation, VMAP, which stands for vectorized mapping, and PMAP, which is parallel mapping. And we'll go through what each of these do and why they're important. So first off, automatic differentiation. Again, this is super important for ML. It's how we do all of our learning and updates. What Grad will do is it will take some sort of function that is going to return a scalar value. Typically, this will be your loss function in any sort of ML training. And then we can easily wrap it in our Grad function here. This will return a new callable function that we can then pass through and retrieve the gradient from. There's also a version that will give you the value on the gradient, which is important when we're trying to do loss calculations. But as well as that, we can continue to just compose these functions on top of each other. So if we want to do higher level gradients, we can just keep wrapping it in the Grad function to get higher and higher orders of the gradient. As well as that, we can combine any of the other transformations together. So any of the transformations we see going forward, you can all just compose them to get extended functionality right out of the box. So next up is the JIT compilation, which is just-in-time compilation. This is the function that is actually going to compile your functions down to XLA. And this is going to be very fast for all the reasons we briefly talked about for XLA. So in the example here on the slide, we have some sort of matrix sum, which is multiplying and then summing it up. We have two examples. One using a NumPy matrix, 5,000 by 5,000, and then we have XJMP, which is going to be the Jax version. So Jax has its own version of NumPy, commonly labeled as JMP, and it basically provides all the same functionality as NumPy, but on accelerators. And we can see that when we do different timing functions, without jitting this from the start, carrying out the mat sum on NumPy is about 151 milliseconds. Doing it with the Jax version is 109 milliseconds. And then when we JIT compile this, that brings it all the way down to 17.8 milliseconds. So roughly, Jax is almost 40% faster than NumPy originally. And then when we JIT that, it has a massive speed up of about 8.5. So JIT compiling is really, really good for speed. Next is VMAP Vectorisation. So we're getting into the realm of scaling up and parallelizing our work. So for ML in general, we are working with large matrices, and we want to carry out our matrix manipulation in parallel as much as possible. Jax makes this really, really easy with the likes of VMAP, and it lets us automatically vectorize these computations. So on the right here, we have a very, very simple function, minmax, which will take in a vector and it'll return the min and the max of that. So that's great. If we want to do a batch of these vectors, then we need to, usually we need to change how we're doing this calculation. So we can write a new function that is going to do, basically manipulate the axes to quickly generate the min and the max for a batch of vectors as opposed to a single one. And that's fine, and that'll be performant and that'll work. But instead, what would be much easier is if we can just write our single function that is built to work on a single piece of data and then automatically scale that for batches of data instead. And VMAP lets us do that. So at the bottom, we can just wrap our original function around VMAP, and this will automatically vectorize it across our batch of data in parallel. And then we have PMAP, which is essentially the next step for parallelization. PMAP is going to JIT compile your code. It's going to replicate that function across your devices. So if you're running with multiple GPUs or multiple TPU cores, this will replicate it out to all of them. And then it's going to execute your function on those pieces of data in parallel across your batch. So again, this is obviously very, very useful when we're training models. We want to split up our batch into mini batches and then carry out that computation across multiple devices. So you can see here we have a very, very simple dot product example. We want to take in, let's say, a batch size of 8 or 8 matrices, and we want to calculate the dot product of all of them. If we're to do this sequentially, we need to iterate over them and calculate the dot product and append it to our results. There probably is better ways of doing that, but for this example, we'll run with this. And that's taking about, 350 milliseconds. Instead, again, the whole pattern of Jax is that we want to write our functions as if it is just going to run sequentially, and then we want to automatically scale it up. So with PMAP, we can do this. We can have a very simple function, and I lazily just wrote a lambda function that is going to do a simple dot product, and then we can wrap that function in a PMAP for it to parallelize the whole thing across the devices we have. And for this, it reduces the time down to 115 milliseconds. So I realize I'm going through this very, very quickly. The main thing you need to kind of keep in mind is that Jax's whole design process is to write your code once as if you are training or as if you're doing computation on a single piece of data, and then automatically scaling that up to multiple devices, whether it's GPU, whether it's TPU, or it's something more proprietary. So that all sounds great, theoretically. But what is it like to work in Jax, and what are the things you need to know to work in Jax? First off, in order to be able to do this and train very, very quickly and run very, very efficiently, you need to be able to JIT compile the things that matter. And for that to work, your functions have to be pure functions in order to work reliably. So that means a few things. First off, your output only depends on the input and not shared state. So for most people who are comfortable working in object-oriented programming and stateful programming, this is going to be a little different. You cannot depend on stateful objects or stateful functions because that is going to break your compilation. Next, the same input always has to give you the same output. And finally, no side effects from calling a function. If you do something in your function, it has to return you updated state. You can't call a function and then just randomly update global state at some other part of your system. So for those of you that are familiar with functional programming, this will be like your bread and butter. If you are used to object-oriented programming, this is going to take a bit of time to get used to. But once you do get used to it and you are doing more experimental research, when you're doing things that aren't quite standard in ML, this is significantly easier to work with and is much faster to work with, and it's a lot less error prone. And that's, again, one of the main reasons that Jax excels. Next up is RNG. So Jax uses a modern explicit pseudo-random number generator, making it very easy for it to be reproducible. Most frameworks use global state random number generation. So basically, anytime you are using random functions anywhere within your system, you can call and update that state, and it's very easy to kind of lose track on who is calling what and what sequence of ordering the state is being updated and changed. Once you then move to like a distributed setting, this is going to make it harder and harder to make sure that everything is reproducible. So in Jax, it is a little different. So on the right here, we have a very simple example of how to handle randomness in Jax. The method that is used is going to generate some sort of pseudo-random number generator key based on your seed. This is our random number state, and we are going to have to maintain that and pass that through explicitly when we want to use it. So our second line here is we are doing random.normal, which is just going to put out a random number. And you see that it takes in the key. If we pass that in and call it, we are going to get some random number. If we call the same function again with the same key, which is our state, it is going to give us the exact same result and be completely reproducible. If we want to update our state, we need to split our key into subkeys. And this is going to be our new state that we are passing to our functions. So if I call random once, I pass it the key. If I want to then call it again and have it be a new random number, I need to split that key for the function that it is using. This is going to seem a little convoluted at first. It's going to be a little tricky, but when you get used to it, it is much easier, and it is much easier to reproduce and show exactly what you want. When you run training plots in Jax and it is the same and nothing you have done has changed, it will always look the exact same to the point. And finally, control flow. So again, the whole thing with Jax is that things are jittable, and that is going to be compiled down so it can be executed really, really fast. There is some constraints around control flow for this point. So when you compile your code, Jax is going to trace everything in, and your functions are going to be converted into what's called a shaped array. And that's basically saying that Jax knows that you are going to take in some sort of shaped array, and you know what shape that will be. You don't necessarily know what value that will be. So if you try and do an evaluation on that shape, it is going to freak out because it really doesn't know how to do an inequality or how to evaluate. So in the example here, if we say x is less than 3, Jax doesn't know what that's going to be. We can't carry that out when it is compiled. However, there is ways around to work with this if you need to do this, which there's a good chance you will. And that is by, when we JIT it, that we can set static arguments. So we can basically tell Jax, okay, this is always going to be a certain value, and we are not going to change this. Once we have compiled our code, this is going to be the same for what we want, and now we can say that this shape isn't going to change. So it can say, okay, we know it is within this range, so when we compile this and run it, it can be within, it can have this level of certainty that it is going to, well, for the example here, it's going to be less than 3, so it's going to be a single shape that we can do this evaluation on. If we change that, it is going to have to then recompile to adjust to that. So as long as you know that your shape is always going to be the same, you can set it as a static argument, and then you know that you can compile it correctly. The next thing that it is, next, I guess, sharp bit with this is if you are generating shapes or generating data in your function. So again, in this example, we can see that we are generating a vector of 1s for a certain length. So if we have no idea what that length is going to be, we are going to have issues with it, and it is going to either recompile or it will potentially break. But if we say that, okay, we're going to set a static argument that the first input is always going to be the same, but the value that can change, then that's okay. Jax knows that it is going to create some vector of 1s for a certain shape. And that is okay for the compilation, for compiling it, and the value can change, but again, it needs to know that you are going to be within a certain shape for it. That, I do appreciate that that is like very hard to kind of wrap your head around, and it sounds really constrictive. And this is kind of the trade-off with Jax, is that it can be super, super fast, but you do need to think about how things are going to be compiled. You need to think about what explicitly you want your functions to do. And if you're able to work within that domain, it is going to be very, very fast, and it's going to scale very, very quickly. And to help with this, Jax provides 4 primitives for handling control flow. The first one is cond, which is essentially Jax's version of an if statement. While, it's a while loop. For I loop, it is for I in range. And then finally scan, which is Jax. It's a unique function for Jax, where this is basically going to take some function and is going to call that function across an array of data. So if you know that you have X amount of data, you can then scan a function over that. So that's a very, very quick run through of working with Jax. Like I said, there is a bit to get used to. Once you do, it is very, very fast and very, very nice to work with. The Jax ecosystem. So it's not as mature as PyTorch and TensorFlow, but it is growing very, very quickly. So Jax Libraries. Google and DeepMind have put in a huge investment in building this up, and they have already put out a lot of very useful libraries to use within Jax. There is low-level libraries for basically handling things like opt-axis for your optimizers, distracts, distributions. JMP is for mixed precision training. There's different frameworks for building neural networks, and some even like PyTorch Lightning style high-level frameworks. Domain-specific stuff, so Relax is RL-specific algorithms, JRAF is graph networks, and there's lots more of these out there. But the best thing is that you can still use other libraries, tools for this. So for example, Jax doesn't provide any data loaders. Instead, you can still use TensorFlow or PyTorch's data loaders within Jax. Same with checkpointing. A lot of people commonly will use TensorFlow's checkpointers to save their Jax models. Our cool thing is you can actually convert a Jax model into TensorFlow. So if you want to do your training or research in Jax, you can then convert that to a TensorFlow model and use that for inference, for serving, and scale it on from there. As well as that, InstaDeep has actually put out several very cool Jax libraries as well. So Jumanji is our suite for building RL environments fully in Jax. So we use these simulations for training and research, and it all can be JIT compiled. And the great thing about that is if your agent is JIT compilable and your environment is JIT compilable, you can now JIT everything in your training loop and run it super quick. Very, very quickly, QDAX is for quality diversity and neuroevolution. CADX, contextual bandits. ManyFold is a Jax-based library with different implementations of AlphaFold and training scripts. And then Mava is our distributed multi-agent RL framework. I would encourage you to check those out and contribute if you feel the need. Next up, Jax use cases. So, just spoke about ManyFold, and at the start of the talk, one of the biggest breakthroughs this year was from AlphaFold, adding in 200 million known protein structures. And I think Times Magazine announced this week that it's one of the best it's labeled one of the best inventions of 2022. So, AlphaFold, for those who don't know, it's a very complex system, and it deserves its own talk, and I won't be able to do it justice. The main thing to know, it is a monster to train. It is very, very large. It has been engineered to the nth degree in order to get the amazing results it has, and it requires a lot of resources. Google actually built their second version, AlphaFold 2, completely in Jax from the get-go, and they then open sourced the code. However, they didn't open source the training code. So, one of the libraries that InstaDeep has released is ManyFold. So ManyFold is our Jax-based library that supports training different types of AlphaFold models. There's protein language-based models, and then there's the full AlphaFold architectures. Both are provided in our repo. And there's also 2 papers accepted to NeurIPS workshops this year that are using ManyFold for their research. So the main things that ManyFold introduces, 1, training scripts for AlphaFold, which I would argue is useful. And 2, it also provides these newer versions of AlphaFold that take out very, very high compute parts of the main model. So on the right, you can see these MSA embeddings, which are multi-sequence alignment embeddings. And basically, this is building up a latent embedding with lots of statistics of sequences that are close to the main protein sequence that you are feeding into your model. Basically, this is looking up a massive 2 terabyte database to try and get more information about the protein sequences you are trying to predict from. And what people discovered is that you can actually get rid of that entirely and train a model to predict what this statistic should be based on a sequence that you are feeding into it. So obviously this isn't as performant or as accurate as the full AlphaFold model, but that gap is closing and closing. Right now, 83% of the performance gap has been closed. There's 17% left. But what's really cool is that there's a 2 to 3x speed up using this model compared to the full AlphaFold model. And you can see here on the right, the chart, especially at the bottom right corner, the blue curve is inference time, and as you continue to increase sequence length, AlphaFold is getting much larger, but the PLM, or the protein language model version, is still quite stable. Next up is population-based training algorithms. So one of the papers that InstaDeep has released this year to ICML was around fast population-based training. So very, very quick overview. Typically in RL or even evolutionary algorithms, you can train one agent at a time and put all your resources into that. But a lot of RL is actually not fully utilizing the GPU because a lot of the research at the minute doesn't use massive models like language models do. So there's still some compute left on the table. Instead, it can actually be quite more efficient to train a population of agents all using the same compute. You can do things like train with different weights, different hyperparameters. You can have combined loss functions depending on what you're trying to accomplish with your population, but doing this can be very powerful. One of the papers that was put out from InstaDeep was, instead of having a population of agents train on multiple devices, what if we just do some clever vectorization of updating this population of agents across one machine and one device. And the idea being that we can completely cut out the communication overhead of having multiple agents run across multiple devices. And what we saw is this has a massive speed up. So down on the right here, you can see that some of the results from the training. There's two algorithms at play here. One is DQN and the other is TD3. And these are pretty standard state-of-the-art algorithms within the RL domain. And it was trained on Atari, which is the stereotypical Atari training arcade environment. The other is half cheetah, which is a control environment where you have essentially like a stick figure of a cheetah with only 2 legs training, but it's a pretty standard control problem. So you can see there, the 2 main curves to look at is one, the pink curve at the bottom, that flat line, that is using PyTorch and is fully sequential. And when we compare that to building the same model sequentially in Jax, is the orange curve. So I'm not sure if you can see the mouse, but there's already quite a big speed up from just moving from the PyTorch version to the Jax version. But the big speed up came once we vectorized. So the green line is PyTorch vectorized, which has significant speed ups. But then when we do the same thing in Jax, it has massive performance improvements and massive throughput improvements. The paper reported roughly 20x speed ups on single GPUs compared to other methods, and obviously dependent on the environment and the algorithm being used for the experiment. Finally, the last use case I have is DPAC. So the previous 2 use cases are in research, and obviously, like I said, Jax is primarily a research framework. However, it is becoming more and more mature, and we're also using it in some of our applied projects. So DPAC is an AI solution to handle the cargo load optimization problem, otherwise known as the 3D bin packing problem, which is NP hard. So DPAC utilizes reinforcement learning to build more robust and scalable solution that is able to adapt to changing environments. So for those of you that aren't familiar with reinforcement learning, basically what this is doing is it has this iterative training loop. We'll have our agent take an action in its environment, whether simulated or real, and for this case, it'll try and take the next object to pack into the bin efficiently. The environment will then update its state, in this case just moving an object into the container, and it will give it back a reward. If it does well, it'll get a positive reward. If it does poorly, it will get a negative reward. And by doing this iteratively, the agent is able to find optimal solutions across a broad range of circumstances for its environment. And what's really cool is, like I said, we can now utilize one of our other repos, Jumanji, which has a version of this 3D bin packing environment completely written in Jax. What this means is we are able to now carry out new research ideas, test and experiment on new stuff in our research environment, and do this very, very quickly, be able to train in a matter of hours instead of days or weeks, and then take that knowledge and start to scale it up to production. And the really cool thing about Jax, like I said, is that if we have our actor, our learner, and our environment fully in Jax and fully JIT compatible, we can compile everything onto individual accelerators. So on the right is an architecture where we have 8 TPU cores, and every core will have its own instance of the actor, learner, and environment, and this is able to carry out computation much faster without needing an overhead of any of the have to go between the accelerator and the CPU and back. So I think I have 4 minutes left, so I need to wrap up quickly. Quick overview. Jax is a framework designed from the ground up to easily scale state-of-the-art algorithms. Designed for scale, main things, XLA JIT compilation by default, and provides multiple different composable transformations like Grad, VMAP, PMAP, and JIT. There's a lot of growing support. A lot of more and more conferences, papers are implemented in Jax, and this is typically a precursor to production. And finally, there is a learning curve. You do have to get used to the nuances of Jax before you start seeing the speed up, but trust me when I say it becomes significantly easier to work with than other frameworks, and you will not want to go back. That said, should you move to Jax? So if you are in research, if you are doing like bleeding edge industry work, or if you're a student, master's, PhD, that sort of thing, I would highly encourage you to try out Jax. However, if you are trying to build a stable, robust product, I would advise against it. Jax is still experimental, and it's probably overkill for most things that is just adapting modern ML to. Next one is if you are just learning ML. If you're just learning ML, you do not need to also take on the task of trying to figure out Jax as well as trying to figure out backpropagation. And finally, if you're looking to break into the industry, I'm a little conflicted about this advice. I go kind of side to side on it, but the reasoning being is that there are still a lot more jobs for TensorFlow and PyTorch than there are for Jax. I imagine that will potentially change soon, but if that is your focus, I would say pick TensorFlow or PyTorch. There's a lot more resources out there to get you started, and it might help in the job search. Finally, if you want to get started with Jax, 2 repos I recommend checking out. One is the awesome Jax repo, which has a curated list of tutorials, models, papers, etc. And the second one is the Indaba 2022 repo. So Deep Learning Indaba is the biggest deep learning conference in Africa. And this year, InstaDeep supported hosting it and provided a lot of the talks and practical workshops. And there is a repo with all of the practical workshops there, all written in Jax. I've gone through all of them. They are really, really solid, really, really good practical information. And if you want to learn about Jax or even RL, transformers, generative models, graph networks, any of those, I would check that out. Thank you.
Hey, you mentioned about converting models from TensorFlow into Jax. So can you talk about your experience, how easy it is or how you do that?
Yeah, that's a really good question. So to repeat the question is that Jax is able to convert models from Jax to TensorFlow, and what is the experience with that? So I have had probably mixed experience, to say the least. I've successfully been able to take Jax models and save them and serialize them as a TensorFlow network, and have then been able to do like inference on those networks. I personally have struggled to then retrain that in TensorFlow. I think there are still a few kinks to work out on that, and it is labeled as an experimental feature. I imagine that Google is pushing hard for this sort of compatibility between Jax and TensorFlow, so I'd imagine that'll be much smoother very soon, but it still has a bit of kinks to work out.
Thanks.
Cheers.
Any further questions?
Not really a question, but a comment. You can do excellent interop between Jax, TensorFlow, and PyTorch using this zero-copy format called DLPack. Although I want to use this for the inference use case, but taking a model from one framework and retraining it in another place is a bit of a stretch, I guess.
Sorry, so you're able to what, like train it in one and then move it into another?
Yeah, so I can have Jax layers in a PyTorch model.
Oh.
Yeah. I mean, although the layers are frozen.
That's interesting. Well, do you mind if I, like, what is the motivation behind it?
I think it's mostly in a supervised setting, so we had some legacy PyTorch stuff. Didn't want to touch it.
Yeah. Okay.
Yeah.
Oh, sick. Okay, that's pretty cool. So you're able to have like an old, like let's say an old model in PyTorch, and then build upon that, or have like a new embedding go into it.
Yeah.
That's pretty cool.
Yeah. So I think the frozen model was PyTorch, put on Jax model in front, and as a curiosity, we even tried like throwing in TensorFlow into the mix. That works too.
That's pretty cool. I have not tried to combine anything before, although we have used like TensorFlow modules, like the distributions module, as like a head for Jax, and it works pretty well.
Yeah. On the other hand, this is purely in a supervised setting. I'd imagine reinforcement learning a lot.
Yeah. Awesome. Thank you.
Thanks.
One more? We can just go for one more.
Like PyTorch and TensorFlow have a lot of tutorials and support out there. What's the support looks like for Jax at the moment?
Good question. So the question is, there's lots of tutorials and resources for TensorFlow and Jax, and what is it like? Or sorry, other way around, for PyTorch and TensorFlow, what is it like for Jax? It's pretty good. It's not as mature as the other two, so there isn't going to be as much. But in terms of documentation, it's pretty detailed to the point of maybe it's not as user-friendly to new users as the likes of PyTorch is. To really understand it, you kind of have to dig into it a bit. There's a lot more tutorials coming from the community that are really, really good and that make it very obvious how to do things correctly. So I'd say it's pretty good. I think I've read almost everything that people have put out there to fully understand it, but it's definitely getting better, and I'd say it's pretty easy to self-study and get up to speed with it. All right, thanks very much, and if anyone wants to chat afterwards, please don't hesitate to come up. Thanks a lot.